Alright, this is video 2 of the population videos. The first one you should already watch. This one is actually about a little math, so you should have a calculator out and ready to go. Alright, so unchanged populations. Basically, you think back to Mendel, his work was rediscovered in the 1900s by a bunch of different people, and one of the things that the biologists really wanted to do was to try to figure out exactly how the alleles might increase or decrease in abundance. They wondered if dominant alleles would eventually just simply replace and take over all the recessive alleles. And once again, there's a couple people who did this. The people that did it one was an English mathematician by the name of G.H. Harding, and the other one was a German physician named Wilhelm Weinberg. Now that W is pronounces the V in German, so it's Weinberg. So the Hardy-Weinberg equilibrium, and they actually did this independently of each other. They didn't do it together. So even though the formula is named Hardy-Weinberg, they were actually independent. So good old Hardy's down there, and the Weinberg is right there. And so they independently demonstrated that alleles do not, in fact, replace recessive ones. Their demonstration, what we now call the Hardy-Weinberg principle, the Hardy-Weinberg principle, states that populations do not change unless evolutionary forces act upon, which makes sense, right? Things don't evolve just for the hell of it. They change because of something happens. The Hardy-Weinberg principle holds true for large populations in which individuals mate randomly, okay? And in that, they'll actually force the change in the alleles that are not acting, okay? All right. So here's the old Hardy-Weinberg equilibrium. It's usually represented as an equation, and it's represented as the following: p squared plus 2pq plus q squared equals 1, where the frequency of alleles that are homozygote for one condition, in other words, like being big A, is represented by P. Individuals that are heterozygote, so being big A, little a, would be that, and individuals that are homozygous recessive, little a, are that, okay? That's the formula. You need to know that, should know it frontwards and backwards, left, right, all that good stuff. Give you a second here to write it down. If you need more time, you might want to pause it now. All right, so the Hardy-Weinberg basically is a principle based on the idea that the frequency of a particular type of gene, we can actually determine what's going on. So for example, if you take the boys in your class, okay, divided by the total number of students. Now this is talking about a co-ed school, not obviously prep, we're a little bit different. The P and the Q in the Hardy-Weinberg equals the allele frequency. Remember, the alleles are those individual letters, so that original example is A or little a. It's how many big A's are there in a population, how many little a's are there in a population. And what we see is that the frequency of A allele always has to equal the other frequency must equal 1. So in other words, P plus Q always equal 1. If you remember those two formulas, the Hardy-Weinberg formula, which is P squared plus 2pq plus q squared equals 1, and P plus Q equals 1, it's just simple math. You should easily be able to determine the formula for Hardy-Weinberg. Okay. So how do we apply this principle? That's the next thing. You apply this by making an ability to predict the frequency of a particular allele in a given population. Okay? And once again, you can kind of read through this and how we'll do that. This a lot of times is easier seen in an actual problem versus necessarily understanding it in this form. So kind of read through that. If you need to pause it and kind of spend more time, you can. I'm going to go on kind of more of the importance and how we actually use this formula. All right, what's the importance of this? And this is important. It allows for us to predict the frequency of each genotype in a population. How many people are carriers for cystic fibrosis in a population? How many people are carriers for sickle cell anemia? Okay, we can determine that using this Hardy-Weinberg problem. So here's how we do it. We take a look at a condition. Now, we can't look at a person who does not have cystic fibrosis. I can't look out in the class, look at an individual and say, yep, you're a carrier for that disease, or nope, you are not. What I can tell is if I see a person who is a particular, has that condition, it's recessive, if I know they have cystic fibrosis, I know they must be, in this case, I'm going to use the letters little c. Okay? Now, because I know that, I can do a lot of, I can learn a lot about how many people are actually going to be big C, little c, and big C, because I know that fact. And here's how. I can calculate the frequency of the recessive alleles. How do I know that? Because I know that Q squared equals the frequency of homozygote recessive individuals. Okay? In other words, I know that if I took 1 divided by 2080 would equal 0.00048. So I know that. And therefore, simple math, if I know Q squared equals this, then if I took this like that, I figure that out, I find that the amount of Q in a population is equal to 0.022. See what I did there? How did I get that number right there? All that was from the previous slide was 1 out of 2,080 individuals. That's that number, right? But I want to square it. That'll give me Q. Q equals 0.002. Now, there's a formula. Remember, we learned that P plus Q equals 1. Simple math. P plus 0.022 must equal 1. And in this case, in this given population, right, P equals 1 minus 0.022, or P equals 0.978. In other words, in a given population, in this particular situation, 97.8% of alleles are going to be the dominant trait. Only 0.2 or 2.2% are going to be the recessive. From this, it's asking me to calculate the number of heterozygotes. Now, how do I do that? If you remember from the formula, P squared plus 2PQ equals Q squared, plus Q squared equals 1, I need to figure out the number of heterozygotes. Well, now I know what P is. I know what Q is. All I do is take those numbers times 2. So, 2 times 0.978 times 0.022, and if I were to put that in my calculator, I would figure out that the actual percent of alleles, or people who are heterozygote, are 0.43. In other words, if I were to factor this out, 4.3 people out of 100, or if I want a nice whole number, because 4.3 doesn't actually exist, 43 out of 1,000 people are carriers for cystic fibrosis. Meaning at Creighton Prep, we have 1,000 boys, 43 of you guys are carriers. Okay? That's not going to factor a day in your life unless you happen to run into another person who happens to be a carrier. Okay? All right. So remember, if you can figure out Q, you can figure out P. If you figure out that, you can figure out the heterozygotes. Let's take a look at another question and have you guys. All right. So cystic fibrosis was one condition. Now we're going to look at a condition of sickle cell anemia. Sickle cell anemia is recessive. So 9% of the African population is born with this severe form of sickle cell anemia. What is the percent of the population that will be heterozygote, or big S, little s? Okay. Go ahead and start to work that out. I'm going to give you about 10 seconds. In that time, that 10 seconds, pause it, work this problem out, and then I'll kind of go through it. All right, hopefully you've solved this problem. If you haven't, pause it, try to work it out. If you have not, because you know what you're doing, let's follow along. So it tells us that 9% of the population have it. In other words, 9%, another way to say 9% is 0.09. They have the little s. Or in that 2p, the p squared plus pq plus q squared equals 1, that is that. In other words, it's equal to that. So we know that q squared equals 0.09. Using simple math, I need to find the square root of this. That'll give me q. Take the square root of that, okay? And I find out that the q value in this case is 0.3. All I've done is solve for the number of alleles for that particular condition, okay? Haven't done too much. Pull that a little side, make it a little bit smaller. Now, because I know that, I also know that p plus q equals 1. So p plus, if I were to substitute that value, 0.3 equals 1. I can do a simple formula here. That's going to give me p equals 0.7. Because I know that, I can now calculate the final part. I want to know how many people are heterozygote. And the heterozygotes are those. So I just take 2 times our p value times our q value, and that's going to be our answer. So 2 times 0.7 times 0.3, put it in my old calculator, and what do I end up getting? Okay, I end up getting that person who is heterozygote for the condition will be 40.42, or 42% of a population will actually be a carrier. Okay, all right. Hopefully you got that. Boom. Right as I said, 42% of the population are actually carriers for cystic fibrosis in that hypothetical equation. All right. Here's where your homework came in. Hopefully you watched this video. For next class, do 2 things. 1, watch the next video. Okay, make sure you watch that. The second thing you need to do is answer these 3 questions. Okay? These are all Hardy-Weinberg equilibriums. You should be able to figure them out. Answer these 3 on a piece of paper along with the notes from video 3. That is your homework for next class. A day, this will be due next Tuesday. For my B day guys, that'll be due on Wednesday. Okay, so I'm going to stop the video now. You might want to pause it to be able to work on these. That's all I got. Good luck, and I'll see you guys next week.